Okay, welcome class. Today we are in chapter 4. We're continuing with force and couple moments or force and moment systems, meaning that's problems that have one or many forces, an additional moment or many moments applied to them externally. And what we've been doing is trying to look at how we can simplify those. So today in section 4.7, we're going to look at the simplification of force and moment or couple moment systems. Okay, so what we want to do when we have a problem that has a whole lot going on, it's when we have to pass it along to the next person who's going to design that for as far as strength and finding out the size of the members and what kind of metal or whatever to make it out of for strength. We want to simplify it as much as possible when we pass it on. So what we want to do is simplify it to a single equivalent force or resultant force. So all the forces sum into a equivalent force. So that's going to be summing forces equal to 0. We know how to do that. And also a single equivalent moment about some point. And the way we do that is going to sum moments so we can get the resultant moment or equivalent moment about some point. Okay? Now, 2D, that's going to mean we sum forces in the X, we sum forces in the Y, and we are going to sum moments equal to 0 so we can find the resultant moment about some point. In 3D, no surprise here, we're going to sum forces in X, Y, Z to find that resultant force, and we're going to sum moments about some point to find that resultant moment about a point. Okay? So nothing we haven't done before. Summing moments, summing forces, as I've told you since the beginning of class, are the two things we have to know how to do the whole semester. We're finally at a point where we're going to use both of them to reduce that to a single force and single moment. So let's do a quick one with 2 dimensions, just so we can get the idea of how that's going to work. Little example here. How's that showing up? Showing up all right? Maybe I'll keep the same marker here. Let's say I have a beam here, and it is subjected to a force 2 and a force 1. We have some distance 1 here. We'll have distance 2 here. And what we want to do is reduce that to a single. So we want to reduce or simplify or find that single resultant force and the single resultant moment about some point. Okay? Now we could pick any point on here, and in this problem I'm going to tell you that we're going to find it about point A. We're going to use point A sort of there at the origin, assuming that's where the connection is. Okay, so we're going to find a single resultant force, which is equivalent to all the forces acting on it. And we also want to find that single resultant moment, which is going to account for or be equivalent to all the moments that were acting and also as a result of that force. All right, so finding the resultant force. How do we do that? Well, we sum all the forces up. That'll give us a resultant force. In this case, it's just going to be F1 plus F2, and they both are down, so we have that direction there. We'll just call that FR as our resultant, because we're not putting any numbers in right now. We're just trying to get an idea of what's going on. Now, the resultant moment, since we're told it'll be about point A, is summing up all the moments, which means I have to add the moment due to F1 plus the moment due to F2, accounting for directions. We typically pick counterclockwise as positive. So if I want to have that single resultant force and single resultant moment acting at point A, we already have Fr, so I'm going to put Fr here. And our moment is really just going to be force 1 times D1, that's this way, plus force 2 D2, that's this direction. They're both that direction. That gives us the resultant moment at A. So I would put the resultant moment like this, and I'd label it as resultant moment at A. And that would be our answer if we're trying to find it about point A. Not putting any numbers, just sort of a general one there. All right, so again, our whole purpose is here to take a single equivalent system, meaning we have all forces and moments on it. We reduce to a single equivalent force, Fr, and a single equivalent resultant moment about some point. This is in 2 dimensions, so this is how we do it in 2D. So I'm going to end there, and then we're going to switch over and do some examples of that in 2D, and then I'll do that in the following video, and then we'll move ourselves into 3D. So we'll go back to there. Okay, welcome back. We're in the middle of 2-dimensional simplification of force and couple moment systems, reducing them to an equivalent resultant force and couple moment or moment at point O. In this situation, this problem, we're going to do point O, which is the origin right here. We could pick any other point, but let's start off simple. It'll be point O. All right, so what I have here is my X and Y axes. I have a 60 Newton force here at a 30 below the horizontal at a coordinate of 8, 0. I have a second force here at coordinate 0, negative 3, 0 down at 140. And then I have a moment or couple moment, a steering moment, a rotating moment here at 40 Newton meters at a coordinate of 0, 6. So there's 3 of those. I want to find the resultant force and resultant couple moment at point 0. So we're in 2 dimensions. To find that resultant force, we're going to sum forces. And to find the resultant moment, we are going to sum moments due to all the different forces. So let's start out with the forces first. We're going to sum forces. We want to know in the X and Y direction. So when we go in 2D, we're going to sum forces in the X, and we'll sum forces in the Y. Okay, sum forces in X and Y, and then we'll put it back into our resultant moment with magnitude and direction. Summing forces in the X direction, we'll pick positive to the right. We are going to have 0 for the 140 because that's not anywhere in the X, and we're going to have a minus 60 cosine of 30. Due to that one, the component cosine of 30 is 0.866. So if we go through that, we get 60 times 0.866 is about 50. That's really close to 52 newtons. I think it's just a hair under that if you want to check the math. But it's 0.866 or about almost 0.9, which would be 54. It's a little less than that, so about 52. Summing forces in the Y, we have a minus 140 from that force over here on the left. And we also have a component of 60 sine of 30 due to this force right here. And sine of 30 is going to be half, so that's minus 30. So that gives us a minus 170 newtons, which is really 170 newtons down. And this one is to the right. So there we have a resultant force in the X and Y directions. We can go back and find its magnitude by doing the square root of the squares. And if we go through and do that with the math, we're going to come up with 178 newtons. And I'll leave that math for you to do. But we take the x component, the y component square, Pythagorean's theorem, square root of the squares. If we want to find the angle, just like we do inverse tangent, second tangent, arc tangent, depends on what's on your calculator, what math teacher you had. That's going to be the 170 over the 52. 170 over the 52. And if we do inverse tangent of that, we get 73 degrees. Okay? 73 degrees. Now, that resultant we have as a negative here. So that's this 52 over and 170 down. So that's really giving us that angle right there. So if we want to write that in correct angle measurement, right, we could do this, and that would be the correct, or we'd write 178 newtons at, we'd want to have this angle, and that angle is going to be 360 minus 73, which is what, 290, 287? Yeah, I think that's right. And if not, send me an email. All right, so let's get our resultant force. That's nothing we haven't done before. What about finding that resultant moment? Well, we're going to pick positive to the right. Resultant moment's going to be about O, so we have to include all the moments and their effect about 0.0. Now, the first one is this 40 right here. That's already moment. And if you remember, that's a free vector. That means I can put that 40 anywhere I want. I could put it over here. I could put it at the origin. I could put it here. It's just a general 40 this way. It's not like you have to hold an axle right there, axes, and rotate it right there at 40. It's over the general thing. So that's a free. So that would be the 40 right there. We would add into that. Okay? The next one we could look at is the 140 here. The 140 is acting at 3. That's force times distance. It's going to create a rotation that is counterclockwise. So that would be force of 140 times 3. That's also giving us that direction, so it's also positive. And then what about the contribution of this one? The x component is going straight through the origin, so it has 0. Remember, it's 0 rotation potential, has 0 moment. It's as if we're pushing on the hinges of a door. We want to know the y component. So that's 60 in the y direction. At the 8 will give us that. So we have to add to this. Well, but it's going to create in the other direction. So that's 60. That'll be sine of 30 degrees. That's the force times a distance of 8 meters. And since that's trying to rotate it this way, we have to make that a minus. So these three here, the 40, the 140 times 3, the 60, sine 30 times 6, times 8, those three are the contribution of all this about a moment about 0.0. And if we go through and add that all up, we should get 220 Newton meters. That is a positive value, which means it is that or counterclockwise. And that would be our answer for the single resultant equivalent force and couple moment or moment. That's just a moment or a couple moment because we could have a pair of those to make that, if you remember from previous section. And that would be our answer. So we put that in the box. We put this in the box. Boom, we got that one. There's a 2D problem. All right, I'm going to pause again, and then we're going to come back and do another two-dimensional problem and move on from there. Okay, we're back. We're doing another two-dimensional problem where we're simplifying a system or a setup or a problem that has forces and moments acting on them, whether it's multiple forces, multiple moments, one and the other, any combination. Here we have a truss that I've drawn very poorly, but it is a triangular structure that's 2 feet, 2 feet, 2 feet, 2 feet, 6 feet tall, and I have a 200-pound, 150-pound, 100-pound, and here at B at this little triangle, I have a 500-pound force external acting on it. There are no couple moments acting on it. There's no twisting going on here that's additional to what these forces may set up. But we can see that these forces are this way and this way. It's going to probably tend, since it's fixed here, it's going to trend to sort of rotate this about and kind of create some resultant moments due to those forces, but we don't have any moments on there to add into it. Okay, so again, we're tasked with finding the single resultant equivalent resultant force, resultant moment at point C, which is down here, which is the roller. Again, pinned up here. That would be the proper way to do it. And we have a roller down here. It's always a pin with a roller or a pin with a rocker because we want, if there's any kind of stretch or movement, we don't want this thing to buckle. There's a little bit of slight movement. But again, that's not our class because we're in statics. So I want to find out the single resultant equivalent force. We're in 2D, so we're going to sum forces in the x direction, positive to the right. That'll give us the resultant in the x. We'll find the resultant in the y. We put those back together, find the angle. We have that done. Then we finish up with the moment. So in the direction, the resultant in the x direction, we have to include everything. There's nothing to the 2, 100, 150, 100. There's only to this. That's going to be a 500 acting at that ratio of the little triangle of 4 over 5. And that should give us 400 pounds to the right. Okay. None of these other forces act horizontally. That's the only one that's creating a component that direction. Good. Great. Let's move into summing forces in the y. We're finding the resultant in the y. We'll call it a positive up. Now we have a bunch contributing. There's a minus 200, a minus 150, a minus 100, a minus, that's those three there, a minus this 500 at its component, which is the 3/5 ratio. And that would be everybody that is contributing. We don't worry about, well, what about the pin? Doesn't it resist upwards and things like that? That's considered a support reaction, which we'll look at in a later section and or chapter. We're only looking at the forces they give us. We're not worried about how it's connected. We'll deal with that at another time. If we go through this, that's going to be 3 minus 3, 4, 6, minus 750 pounds, which means it's 750 pounds down. And that makes sense. We expect it to be pulled this way and a lot that way. If we go through and find the resultant here by taking the square root of the squares, I won't write that all out. We're going to come up with 850 pounds. That gives us the magnitude. If we want to find the angle, we'll go here again to inverse tangent, second tangent, arc tangent. That's going to be the 750 over 400. And if we go through that, gives us an angle of 61.9 degrees right there. Now, again, it's okay to say the answer, the resultant force about point C, it's about on the whole structure, is 850 pounds at 61.9. We can say that as long as we remind the grader or the people we're passing this on to that angle is measured from the positive x direction and it's downwards. Otherwise, we'd put in there, what is that, minus, or we put it at 200, what, 98.1? Is that right? And if we left it just like that, we would know that it's measured that way. All right, sort of got cut off there, I apologize. But that's at 61 degrees, right? I wrote that down here. That's 850 at 61.9, making sure we include that direction there. All right, that is the resultant force, equivalent force portion of it. Now we want to go into the resultant moment. And that resultant moment about point C is adding up all the contributions. We're going to call counterclockwise positive. All the moments that add into creating a spin about C. So 200, spinning it that way. 150, this way clockwise. 100, this way. The 500, definitely that way. We'll break that into X and Y and then treat it. So it'll be 1, 2, 3, 4, 5 that we have to include here. So let's start with the 200. That's going to be, again, negative, and it's going to be 200. Its distance here, the perpendicular distance to the line of action of that force is going to be 2 feet. And then we have the minus 150, because again, that's rotating it clockwise. That's going to be at 4 feet. We'll have the minus 100. That's going to be at 6 feet. And then we have the 500. The 4/5 is the X component, right? So that's going to be here. We find that perpendicular distance is this. So that's going to be 6 feet to that. So that's times 6 feet. And then we also have the 500 3/5 component. And that's sort of the Y component of this. That's this value here. And that's acting at 2, 4, 6, 8 feet. And that accounts for the 200, 150, 100, and the 500 X component, the 500 Y component, all force times distance, right? In 2D, we're just going to do force times distance. And they have to be perpendicular distances. And when we add that entire mess up there, we should get about minus 6,400 foot-pounds. And since negative is sort of this way, we're going to write that as 6,400 foot-pounds, and we'll draw it this way. Okay? And give it direction that way. That direction is clockwise. We want to sort of steer away from using negatives. I don't think that's a good practice to be in. Negative just means opposite direction, so we would write it as that, including the direction here, or saying it is clockwise. All right, so another two-dimensional example of finding the single equivalent resultant force and resultant moment or couple moment about some point. All right, we'll take another pause and we'll continue in this video after a moment. Got to erase the board. It takes kind of a bear. That's the worst part about this. We're going to erase the board. We'll come back and we'll just talk about what we do for three-dimensional problems and how we find equivalent force and resultant couple moment in 3D. All right, we'll be back in a jiffy here. Okay, welcome back. We are now looking at a three-dimensional problem and finding the single or equivalent force and moment or couple moment to reduce the system down to a single force and moment. That's really what we're trying to do here. Now we have it in 3 dimensions. I hope you can see this drawing of my 3D drawing on a 2-dimensional surface with a 1-dimensional writing instrument. All right, so what we have going on here, we have a moment up here. That moment technically should have that little curly around it to know there's the moment axis, there's the spin of it, and we're told what that value is down here at the bottom of the board. And we also have a force over here out at coordinate or point A, and we're told what that force is. And what we want to do is find out if everything was moved essentially and analyze its effect about the origin, what would be that resultant force? What would be that resultant equivalent moment? Okay. Same thing in 3 dimensions, except we're going to sum forces now 3-dimensionally, and we're going to sum moments also 3-dimensionally. So we do X, Y, Z, and moments about the X, Y, Z, but we can do them all in one shot. Okay. So what's our approach? Well, we got a force, we have a moment we have to deal with. The first thing I like to do, since we have some coordinates going on here, I'm going to write down what the coordinates are. I may need them, I may not. But in case I do, I'd rather look at the coordinates to do the math than to try to keep pulling them off the drawing. So if I go ahead and pull these coordinates off, A is going to be, what's that, -6. Minus 6, 5, and +5 meters. And B, which is over here, will be a, -3, -3, -4, 3 meters. Okay? And that's just so I can, if I have to build a position vector, since I'm doing a moment, I need to do R cross F, I'm going to have to do a position vector from O to A. It might be easier to pull these numbers this way. All right, first step, let's look at the resultant force. Resultant force is going to be adding up all the forces. And this one's a toughie because I have one force. I'm given it in IJK. We like that. So if I add that force to all the other forces that don't exist, I'm going to end up with an 8, a 6, an 8 newtons. Simple as that, okay? If there was another force out here, pulling down here at point C or something like that, another force, I'd have to add the IJs and Ks and find that resultant force. But if this is the only force, that's easy, okay? Make sure that goes in the box. Make sure it does units. It's already in IJK. We love that, so we can keep it there. All right, what about that resultant moment about C? Well, that's going to be adding up all the individual moments about C. And what we have there is the moment 1 that's given, right? That moment is given. It's a free vector. Remember, moments are free vector. In 2D, they slide this way. In 3D, they can slide in any direction. So we have that, plus we have to include the moment due to the force about point C. Okay? That's the only two involved. There's one force for that one. The moment we're given, so we go there. So this is going to equal, and since we're given the moment, that's beautiful, -20, -70, 20. We have to add that to, how do we find the moment of a force? In 3D, we have to do R cross F of that force. So that's going to equal that plus, if we go ahead and build our 3 by 3, in here is going to be the position vector. There's the force. I can put the force in there because I know it. It's 8, 6, 8. IJK. If I want to know position factor, which one am I going to use? Well, I'm only given point A, and I want to know it about point O. I don't know why I kept saying point C. That should be a point O there. Sorry about that. We're going to use a position vector that takes me from the origin to point A. So that's position vector from O to A, which means I take the A coordinate minus the origin, which is 0, 0, 0. That makes it easy. So when I go through and do this, I get A minus 0. I get -6 here. I get 5 minus 0 there. I get 5 minus 0 there. That's the whole problem right there. The rest of it is math. I'm going to put the answer here just so you have it. If I go through and add this moment vector with the R cross F of this one, it gives me the net result of this moment plus the R cross F of that one about the origin. And I will come up with a -10, an 18, and it should be a -56. And that should be Newton meters. I don't have to worry about clockwise, counterclockwise, because we're in 3 dimensions. And that gives me my resultant moment about point O. Man, I like that problem. I like that problem so much, I'm going to do this. To remind myself when I'm studying, look at that problem, because that's a great example of how to do that. Now, how could this be different? How could this be a different problem? Well, I'd have a second force, which means I'd have to add another force in here and some forces, and then I'd have to put another R cross F down here into this. But what if I was at point, there's another point out here. What if I want to look at point F over here, right? I want to know the resultant force about point F. Same thing, doesn't change because where that F is doesn't affect that force-wise. It's still trying to pull the whole thing that direction. Where it changes is the moment, not in the moment it's given, but in the R cross F. Down here, I'd have to use F to C. I would have to use that position vector from F to C. I would have to build that, and that's where that would change right there. Okay? All right, great problem. Good one to study from and use. And let me just check here. I believe that sort of finishes us off. Maybe we can do, we'll do one more problem. So let's hang on here. We'll do one more problem. That'll finish up the lecture for today. And just hang with me. I'll get this cleaned off and we'll set up another one. See if I can play the music. Okay, welcome back. Last portion here of this lecture for section 4.7 on simplifying systems that have forces and moments or couple moments. So another three-dimensional problem. We have a pipe assembly here. The pipe comes out here at an angle, comes across, goes up, and we have a force 2 acting, pulling on that end, and a force here pulling at this elbow right there. And I've tried to show some dimensions on that. I'm working on having images come up here so you can see the actual image. But this is really just this problem, force 1, force 2, acting at some coordinates. And I'll just call this, well, that's the origin. We'll call that A, we'll call that B. So if we know the coordinates of those two, that's really just that problem. We have two forces acting at 2 points. It happens to be on this actual structure of the pipe assembly, and we want to know what's happening at O force-wise and resultant moment-wise. We're given the two forces here, which is nice, meaning we don't have to build them. Remember, that was the first exam. We don't have to build those. They're given to us in ENGG, so we can just run with them. Okay? All right, so first thing I'm going to do is I'm going to pull out those coordinates. I know the origin is 0, 0, 0. And we're going to find A. A is going to be 1.5, 2 over, and 0. And B is going to be 1.5 up, 4 over, and 2 up, and that's in feet. Now, I don't know if I will need that. It's just a habit I'm into. Whenever I have points there that don't have the coordinates, I want to write them there so I have them, so when it comes time, I don't have to sort of change what I'm trying to work on and go, oh, well, I needed that, and then find it. That way, I need it, I can go right to it. That's just my way of solving it. If it works for you, great. If not, that's fine. All right, so resultant force. Well, to find that, we add up all the individual forces. We have 2, so I'm going to add those 2 forces together. Not too hard to do. I can probably do that in my head. I'm going to get a minus 30. I'm going to get a 15, and I'm going to get a 45, and that will be pounds, and done. Love that. Don't we love it when they give it to it in ENGG? It makes life super, uber easy. All right. There's it. That's the resultant force. If we had 3 forces, we'd add 3 forces together. If we didn't have them, if they gave us a magnitude and line of action or points, things like we'd have to build them, but nice here they didn't. All right, what about the resultant force? Make a little bit of room here. About the resultant moment, okay? The resultant moment about point O is going to be the moment due to F1 about O plus the moment due to F2 about O. So that means we're going to have an R cross F for the 1 plus an R cross F for the 2. Oh, it's not where I wanted to put that. Which R do we have to use? Which position vector? Again, we have to go from the point of rotation or what we're asked to, which is the O origin, to the point of application. So this is going to go from O to A. And for the B, since it's about O, I'm going to use a position vector that goes from O to B. So there we can see how those coordinates are going to be important for us to build that. Okay? But let's see if we can sort of build this into 3x3s right off the bat. I think it would make life a lot simpler if we can. But if you show this much on an exam, I can see exactly where you're going, then I can check numbers. This is the F1, R cross F1, so I need F1, which is down here is minus 20, minus 10, 25. And for F2, we're already given that, so that's minus 10, 25, 20. Now we just have position vector from O to A. O to A, or 0 to A, is that minus 0, 0, 0, so that becomes easy, 1, 5, 2, 0. Same thing for B, that's 1, 5, 4, 2. And that's it. That wasn't so bad at all. I mean, it looks difficult. We haven't done a pipe assembly like that, but it's the same process. Some forces, some moments. We have to build the moments. And if we go through this, I'll just give you the answer here. You're going to end up with an 80I minus about 88 in the J and a little over 102 in the K. That's going to be pounds foot or foot pounds. And there is the equivalent resultant force and resultant moment about 0.0 done, and done. The only way that problem changes is if we want to know the moment about some other point, some other random point, we would have different position vectors. Nothing else would change. Nothing else would change. So another really good problem. This is in 3D. And that would actually close out section 4.7 on simplifying these. And where we go next then is, can we simplify it even further? Instead of just having a force and a moment, can I slide that force and moment to another point to just have a single force, this single force to do the force, which it already does, and also set it up so it put it at a position or location so it actually creates this moment as well. So now we're down to a single force that does all of this mess. And it makes it super easy when we pass it on to the strength people, when they want to start designing these pipes and the thicknesses and the steel and blah, 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 blah. Okay? All right, so good one there. I hope this worked out for you. This is one of my earlier, actually my first real lecture video using this e-glass. So if you've made it this far in the video, I'd appreciate any comments. You know, be nice. I'm just getting started. But anything constructive that maybe I can tweak to get better. My handwriting can't do much about. I'm trying to put the images so you know that we're in statics, and you know, I can throw some music in there if it's on there, and hopefully that worked out too, and hopefully the audio is coming through. So, all right, that finishes up 4.7. Have a great day, and we'll talk to you later.